In part 5 of survival analysis of SPSS, we're going to continue to explore the Cox regression method and look at how it performs when we're working with multiple predictor variables. So returning to our earlier example, we're going to call up the dialog again for Cox regression by going to Analyze Survival Cox regression, and here we can see the same settings as before with the variable retire, the only variable entered into the independent variables box, effectively a predictor variable. We saw that that was statistically significant, and we can see it's been set here as a categorical field. Let's add some other fields in to see the effect on the model. I'm going to add in the variable which is continuous in this case, toll-free last month, which is the amount of time spent on toll-free calls in the previous month. And I'm also going to add in this variable which we saw in live tables, which is the customer category variable. Notice that when I add it, because it's already set up as a nominal field, it will automatically see it as a categorical variable. But if I wanted to change what the reference category was, I could do so by clicking on categorical up here and changing it, and I will do so. Currently, under the current default settings, the value of the lowest code is the reference category, so that means we will get binary coefficients in our output that show the effect of being an e-service rather than basic service, the effect on survival of being in plus service rather than basic service, and the effect on total service rather than basic service. Well, I'm actually going to reverse this and say I want total service to be my reference category, so I'm going to click on categorical up here, click on this contrast type indicator, and just say the last group should be the reference category. So that means everything's going to be in reference to total service. And is there anything else I can do at this stage? Well, actually, something I've switched on is I switched on display baseline function. That will actually provide additional output in the form of a bit like a life table or the sorts of survival tables that we were seeing in Kaplan-Meier. Okay, let's click this and run it. Oh, just before we do so, I'm going to change the plots. I'm going to go into the plots here, and I'm actually going to ask for separate lines, not for the retirement variable, but for our new categorical variable, which is customer category here. So I'm saying, show me these hazard plots for the 4 separate customer categories that people are in. Click OK, and let's look at the results. So once again, we have our case processing summary at the top here, which you've seen before. We also have a little reminder here telling us how the categorical variables were coded and which one was the reference category. So retired still there. There's customer category. And we can see that total service is the reference category because it's got codings 000 across. So it's the group to which all the other packages, all the other customer categories are compared. Then we have our -2 log likelihood, which is basically showing us the fit. The larger the value, the worse the fit, without any variables entered into it. That's why it's called block 0. Then block 1, everything gets entered in one go. So the change from the previous step and the change from the previous block are the same because it's entered in a single step, it's entered in a single block. And it's saying that, yeah, this is making a significant improvement upon the -2 log likelihood. In fact, we can see here that the jump here from 3,526 down to 3,438 is bigger than the one that we saw earlier on, where we saw with just retire, just using one variable, it goes from 3,526 down to 3,505. So, a much more modest decrease of about 21, whereas here we're seeing a much larger decrease of 3,526 down to 3,438, nearly a decrease of 100. And then we have our variables in the equation coefficients table. Here we can see that because retired is not the only variable now, it's not the only coefficient in the model, it has to control for the presence of the other variables. In fact, you may find that if the other variables are very collinear, or they are functions of retirement, you may well find that retirement is no longer statistically significant. In this case, it is statistically significant. The b value has changed somewhat, and therefore the exponentiated b value has reduced somewhat, 5.487, because we have other variables in here which are helping us to predict the outcome, and they're taking some of the predictive power. So toll-free last month is a continuous variable. It's not split into binary groups or anything like that. It's actually a minus beta coefficient here. And that means that the exponential b-value is less than 1, meaning that as toll-free increases, in other words, as people spend more time on toll-free calls, the likelihood of churning reduces. Now, it's just under a value of 1. Remember, if it was a value of 1, it would make no difference whatsoever. It would mean that it had no effect whatsoever on the survival rate. But it's slightly less than 1, and that's basically because we're talking, of course, about the effect of a 1 unit change. Now, a 1 unit change from retired to non-retired is the effect of that entire variable, whereas a 1 unit change in toll-free calls for the previous month, let's say a value of 33 to 34, is actually less than 1% change in that variable. So it's a much more marginal incremental effect. It doesn't have as dramatic an exponential b value, but nevertheless, it's a statistically significant contributor to it. And then we have our customer category variable. Customer category here is shown to be statistically significant. Overall, it's statistically significant. And then we have customer category 1, 2, and 3. It just adds the numbers 1, 2, and 3 to them, irrespective of their coding. So if I go to utilities variables here and just call up customer category, you can see here are the values for customer category. Remember, our reference group is total service. So it's saying, what is the effect of being in customer category 1, which is basic service, compared to total service? Well, that value is greater than 0.05. So we're actually saying that statistically speaking, there's no difference between basic service and total service in terms of your overall hazard rate, if you like, what the chances of survival are. It does have an exponential b value, which is a fair bit less than 1, but it's not statistically different. Whereas customer category 2, which is e-service, is significantly different from total service. And the customer category 3 here, which is plus service, is also statistically different from total service. So we would expect total service, therefore, given the fact that all these values have exponential values compared to total service of less than 1, we would expect total service to be the group with the worst survival chances, if you like, where people are more likely to churn. But one where basic service is not statistically different from one another. And we will see that in more detail once we get to the actual hazard plot. Now, you remember that I did request in Cox regression here, I actually went to options here and I requested a baseline display baseline function. This gives you a baseline cumulative hazard. So it's just like the survival tables that we saw earlier on, and proportion of survival, proportion of cases surviving at that stage. So it shows you what the baseline is, and it shows you what the hazard is if you take the average of the covariates, the mean of the covariates. So it's basically saying in the presence of the covariates as opposed to independent of the covariates being our predictor variables. So that's why it's a slight difference here between one and the other. If we scroll down here, get to the end of that, we then get to some covariate means and pattern values. This is basically, these are just averages, just basically some averages here and showing us how these values have been coded effectively over time, but not terribly interesting. The average for toll-free time spent in the previous month is 13.2, it so happens. And here's the hazard function at mean of covariates. So this is basically this value here where we're looking at the cumulative hazard, where we take the average across the covariates, as if you're trying to create a sort of typical average case, the most typical case in the data set. What would the hazard function look for that really typical average case? And then we have our hazard functions for patterns 1 to 4. Now you remember that I said that we expect total service to be the most hazardous, the one where you're most likely to churn, and sure enough, there it is. It's the top line here, total service, much more likely to churn than these two groups down here, which are very close to each other, e-service and plus service. They're much less likely to churn because we can see that their cumulative hazard plot is at a much shallower incline. We're not seeing the same proportion or the same rate of churning. And then we have the middle group here, which is basic service. And basically what we saw earlier on was that these two groups are not statistically significant from one another, but this group is statistically significant from, of course, plus service, and total service is also statistically significant from e-service. Okay. So that's all very interesting. We've seen that we can add additional variables in. At this stage, we could return to it and add more variables in. We could play around with stepwise, or whether or not, which if you're familiar with regression, allows the system to choose the most significant predictors in order. But it gives us an idea of how to interpret, particularly the coefficients table, when we're dealing with multiple variables. The question one might ask at this stage is whether or not some of our assumptions hold up. You remember that we have this assumption about proportional hazards, and earlier on we ran this routine and we looked at, for example, the relationship between retirement and non-retirement, and we got this type of plot coming out when we looked at the means here. We got this plot, and you might look at that and say, are these two, is the survival rate proportionate for these two groups? Is it affected? Does it change over time? Because they should be proportional for one another. Well, there are certain things we can do to actually test that assumption out and check it, and that's what we're going to look at next. So one way to test the proportional hazards assumption is through a visual assessment, and what we would do is we'd go to analyze, back down to our Cox regression, call that up, and if we wanted to visually assess whether or not, let's say, the variable retirement met the proportional hazards function, then what you do is you would actually make that a strata variable. So if I made that a strata variable, what that would mean is it would actually fit two separate baseline functions. And then if you go to plots, you could ask it to plot what's called a log minus log chart, and that basically allows us to then compare the two different baseline hazard functions in the presence, of course, of our other predictor variables. And if they look roughly parallel to one another, you might say, and it is somewhat subjective, you might be able to say, well, it looks like the proportional hazard assumption is met. Now, unfortunately, with retired here, we don't have very many cases in the retired group, so it's quite difficult for us to do that. Let's just click OK and look at the result of that. So you can see here's the same results we got beforehand. You can see it's very difficult here because the we just don't have very many cases in the yes group. It certainly doesn't look like it's parallel, but it's hard to assess at this stage. If we compare and contrast that, let's try a different one. Let's assume that we were actually interested in the customer category, this one here, the customer category strata. Click OK at that point. There's a lot more cases in here. Look at that one. Okay, now you can see that because we've got more data, do they look like they're parallel to one another? Well, there's some sort of crisscrossing occurring here. It's difficult to say, but this is one way in which people actually try to visually assess whether or not the proportional hazards assumption is met by actually creating separate hazard functions and then using a plot like log minus log. Some people use survival. Log minus log kind of straightens it out as a way to assess it. Now, there's another method we can use, which is we can build a different type of Cox regression model, and one which incorporates time as a function, if you like, of the covariate itself. Let's have a look at how that's done. So Cox regression can actually be extended to incorporate what are called time varying or time dependent covariates. And often this covariate is basically a variable that by its very nature tends to vary over time, such as people's blood pressure or the weight. And it does this by creating what's called an interaction term. An interaction term is something that combines one variable with another. And in this case, we'd be combining time as a variable, as a measure, with the predictor field of interest. In this case, we might be looking at, say, retirement. Now, if I go to access it and go to analyze down to survival, and you'll see there's Cox regression, there's Cox with time-dependent covariate. And this expression builder appears. This is kind of not what you're expecting to see, of course, because you're expecting to see a Cox regression dialog. But this is really allowing you to set up the time variable beforehand. This is what this is focused on. The time variable is actually a system variable here, which is t. And what sorts of things might somebody do here in this expression builder to it? Well, some authors suggest you take the log of time if you've got really, quite a lengthy, maybe skewed distribution of time. You take the log of it. Others suggest that maybe you notice that the divergence occurs after a certain time point. Let's say after 100 days, in which case you can say, time. I'm only interested in time after a value of 100. And seeing if there's an interaction effect there between time and the independent variable at that point. In this case, I'm literally just going to take t for time. That's all I'm going to say. I'm not going to do anything to it. Just going to leave it as is, and then click on model. When I click on model, suddenly we get into this realm where we have a Cox regression dialog that we saw earlier on. I'm just going to hit reset here to build this up from scratch, so you can see how it's done. And I'm going to start off, of course, building it by specifying the time variable, which of course is tenure, specifying our status variable, which of course is churn, which is 1, and then I'm going to enter, just as we did right at the start when we introduced Cox regression, introduce the retire variable at this point. And what I'm going to do then is create the interaction between retirement and this time variable. I'm going to actually create a separate block for it, so they're not going in at the same time as the retirement variable. It's going in a separate block. If I hit that point, here is the time variable, which is just t underscore cove here, which is this time. And then we simply click on retire at the same time using control click here. If I click this little button here, this creates an interaction between the two. And if I click OK at that point, I can see whether or not this is statistically significant in the model. And if it is statistically significant in the model, it kind of indicates that the proportional hazards assumption has been violated, because with this time as or retirement as a function of time, is significantly contributing towards the model, which would indicate that it does indeed violate the proportional hazards assumption. We couldn't really assess this earlier on when we were looking at the log minus log, because we just don't have enough examples of retirees. We click OK at that point. And here it says, okay, here's your omnibus. It's saying change from previous step, change from previous block. What is happening here? Well, if we look at it, we can see that retired is no longer significant, and that t as a retired as a expression, as a function, if you like, of time is also no longer significant. So the presence of this variable has kind of negated the retirement variable. But it's basically indicating to us that, that at least retirement as one of our predictor fields doesn't violate that assumption. Is that true for the other two variables that we had? Because we were looking at toll-free calling, and we were also looking at the status variable, what type of package on. Well, we'd need to then rerun the analysis, including them as a interaction with time, to see what effect they have. So let's have a look at that. So returning to that dialog earlier on, we just go call up the compute time dependent covariate, hit model again. There's block 2. Let's add in the other variables at this stage. You can see retire is actually, we should set it up as categorical as we did beforehand, and say it's actually the last group. Just try to recreate everything as we did last time. We've got this variable down here, which of course is customer category, which we're going to put in there. And once again, we're going to set that up where the last group is the reference group, and then we're going to choose our variable here, which is toll-free calling in the last month. Send that in, and then we're going to go to block 2. We'll go to block 2. We'll send these variables in again, so we're going to send them in again, but this time use them as interactions against the time covariate. There we go. So this customer category interacting as an interaction term with the time covariate. Do the same thing here with toll-free calls and time covariate, and they're in a separate block. So there we have the first block, everything going as normal. Second one, all the time covariates going in. It just makes it easier to interpret it. If we click OK at that point and just scroll down to the results here, we can see that we actually get the first block. This is what we've seen already, where customer category's been entered, toll-free calls last month, and retired's been entered. And they're pretty much all statistically significant, apart from, of course, the contrast, as we know, between customer category 1 and the reference category, which is the total the total package. What we haven't seen in this block is we haven't seen the time varying covariates being added in yet. So let's see if they're statistically significant when we look at them at this point. And remember that these are just being forced entries. Let me just extend this out so you can see it a little bit clearer. So you can see all the time varying covariates been added in here. There's retired, that's not statistically significant. Customer category overall is not statistically significant, and none of the individual contrast terms are statistically significant, and toll-free call last month is also not statistically significant. So it's looking at this stage, you know, and we are using forced entry here, we need to do some further testing, but it's looking at this stage that these variables are not functions of time. They don't violate that proportional hazards assumption over time. So we could progress if we wanted to with the standard Cox regression model based upon this evidence.